Hello folks, I want to solve some torque problems on this video. First of all, I want to review what torque was. Torque was the rotational effect of a force. To find the torque, we either take the component of the force perpendicular to the distance to the pivot point about which the objects rotate, or just take the extension of the force and draw a perpendicular line to the pivot point, calling it R perpendicular. So either R times F perpendicular or R perpendicular times F, and both gives the same values. So distance times force times sine phi, phi being the angle between the extension of R and F. There were two important facts about the torque. One, we could have a zero torque. We say tau net is zero, what we call rotational equilibrium. Then we will look at all the torques that are rotating the system counterclockwise and equate them to all the torques that are rotating the system clockwise. Traditionally, we take counterclockwise positive and clockwise negative. It's totally fine to switch those, but we'll stick with the historical approach. Second, it could be a net torque. Net torque might not be zero. Then we say this net torque is equal to I alpha. I being here the moment of inertia described up here, and alpha being the angular acceleration. Let me rewrite them. Alpha is angular acceleration, and the unit of alpha will be rad per second squared, and I is moment of inertia. I is going to be given for us as an equation or a number, but is generally directly proportional to mass times the radius squared, and its unit will be kilogram times meter squared. This example here is showing we could have a situation where we have rotation in this direction. In this case, we will have a clockwise torque net, right? And this torque net would be equal to I alpha, or we can solve for alpha, angular acceleration, not net torque over moment of inertia approach. We can reach to linear velocity and acceleration using angular acceleration and actual definition of angular velocity, which we didn't do yet. Linear acceleration will be angular acceleration times R, and linear velocity will be angular velocity times R. We can easily define angular velocity as how much in angle object spins in a certain time. That would be angular velocity. Here are a list of moments of inertia for common shapes, and I'm gonna solve some problems now. First of all, I'm gonna go back and solve a simple problem over here somewhere. We looked at this already. I'm gonna resolve this problem. We have a force applied by a muscle here, which is called Achilles tendon, and this force is given as 720 Newton, shown in here as well. So this is our F. And we're asked to find what is the torque this F applies to the ankle point here. So this would be our pivot point. This angle here is given as 55 degree, but we're looking for this angle, which will be our angle with respect to distance from the pivot. Actually, angle between the distance from the pivot R and the force here, and that will be 90 minus 55, that would be 35. And the question tells us the distance r is 3.6 centimeters. So we'll find our torque as force perpendicular times r. This will be r times F times sine phi, and this angle we calculated here would be phi angle between F and R. Tau would be then 3.6 centimeters. Let's convert that to meters. R is 3.6 centimeters. Divide by 100, that will be 0.036 meters. We put that in here. We can again drop the units. I just like put in the units. 720 Newton is the force times sine 35 degree. If we do this, we'll find a torque of 21.23 units. For torque is just Newton times meter, no specific name. And we can all see, hopefully, we can all see that this direction is clockwise. If I wanted to give it a direction as plus and minus, I will be minus in the historical approach. We talked about how an equilibrium should be in two ways. For equilibrium, total force, or F net, would be 0. So then we say A is 0, all right forces cancels left, all up forces cancel down. Now we add one more, tau net, torque net should also be 0. Then we will say all clockwise rotations will cancel all counterclockwise rotations, and we'll say torque is 0. This question is asking us if this object is in, which of these objects is in static equilibrium. It would be this one only. We have two forces to the right, one to the left, twice large as the either force. So forces cancels, no acceleration, right or left, and there's no rotation either. This guy is not in equilibrium, for example, because, for example, forces are canceling again, but this guy will cause a rotation. In this case, forces do not cancel. In this case, forces do not cancel, plus a rotation happens in this direction. So the last one, D, is the stable one. In this question, we have a strong man lifting up a weight. So he has a force, let me call this F, and he applies a torque to this pivot point here. I'm going to call this distance R1, so R1 and F1, and he is lifting up a weight. This weight, let me draw that better. This weight I'm going to call mg. I like calling weight mg. So now I'm going to give it a name. This will be my force 2. It will also have a distance to pivot, and I'm going to call that R2. So the question is telling us that strongman competition uses an old-fashioned device to move a large load with only muscle, a 910 kilogram bucket. So we know the mass of the bucket, 910 kilogram. We write it down. Suspended from a sturdy lightweight beam. So beam lightweight means ignore the beam mass. So ignore beam's mass. That's what it means here. Otherwise, we'd have to show mg of the beam from the center of gravity, but we ignore it in this case. The man lifts a lightweight beam 0.85 meters from the pivot, so R2 here. Let me write its value on just beside it. R2 is 0.85 meters. The man lifts the beam at its end 3.6 meters from the pivot, but I read from here as R1 is 3.6 meters because it says the man lifts the beam at 3.6 meters away. So he applies his force 3.6 meters away. He holds it steady. That means the guy is trying to rotate the system clockwise here. And mg, the weight is trying to rotate it counterclockwise. And these two torques cancels each other. So I'm going to redraw this guy again here. This F1 would rotate the system clockwise. So tau 1, if we like, will be clockwise. And tau 2 by the force F2 will be counterclockwise. If I need to show their direction in plus and minus, tau 1 would be minus, tau 2 would be plus. I don't need to show plus and minus here since we have an equilibrium. Steady beam, not rotating, means tau clockwise. I would add all the clockwise taus, torques, and would equate it to tau counterclockwise. I would add all the counterclockwise torques and equate them to each other if I had more, but in this case I have only one clockwise. Tau 1 is equal to 1 counterclockwise, tau 2, and that's it. And what I'm going to do now is apply the torques. F1 R1 is equal to F2 R2. Notice I'm skipping here sine phi because for both of them phi is 90 degree. You want to make sure you see that when I extend this weight up here, it will be 90 degree, and sine phi for both is sine 90, which is 1. So let's also notice that. So I just put F1 R1 F2 R2. Whenever we have forces perpendicular, we can go ahead and do this. I'm looking for F1, so my F1 from here, leaving it alone, will be F2 R2 divided by R1. When I insert all these values which are given to me, my F2 is mg here, I'm going to find the force of the man, and that should be equal to 2105.64. Let's call this A. Additionally, questions asking us what is the force on the beam by the pivot. I'm going to look at that now. Let's do this with blue here. Pivot will apply a force upward. Alright, let me draw that better. An upward force. Let's call this, I don't know, F pivot or F3. I could take a new torque equilibrium using this point, the man to be the pivot. Then I don't have to worry about this force. It will have a 0 torque. And then look at the torque of this new force I'm considering, the pivot force. And the torque of mg would be the other direction with respect to this new pivot point. But I don't have to take that it's longer. I can just go ahead and say F net should also be 0 here, because the object is not moving up or down, right or left. And that means when I add all the up forces, they should cancel down forces. So I can simply say up forces are equal to down forces. And that's it. We are given some techniques here, but it's not necessary to go through all those techniques. What do I have up? I have F1 plus F3. What do I have down? I have mg or F2. So I'm going to solve for F3 by saying mg minus F1. When I input all the values, that should give me 6,812.36 Newton. Following question I have actually is for you folks. This is for you. Consider this. Apply your torque here. Scale would be pushing up, and this mg would be pulling down. Rotation directions will be opposite, and they should be equal to each other. Since I'm applying the mass, the weight, twice farther away, and their torques are equal, this guy should be twice larger. We can also easily find it by logic. This one is very similar to the man lifting up the weight. This lady is jumping from here. We're asked to find the forces the fulcrum and bolt exerts on the board. Bolt will try to pull the board down. I'm going to call this F1, and the fulcrum will try to push the board up. I'm going to call this F2. The lady additionally have a weight mg here. First, use either bolt or fulcrum. I'll go for bolt and use torque in equilibrium. So take this as your pivot point. Take bolt as pivot. Apply rotational equilibrium. So you'll say tau clockwise is equal to tau counterclockwise, and find the force of fulcrum using that. mg will be rotated in this direction. Let's call this F3, tau 3, and fulcrum will be rotating with respect to this point in this direction. Let's call this tau 2. Their distances will be R2 and R3 given in the question. So you will say these are also perpendicular, similar to the man lifting the weight. Very similar question. And you will say then torque 3 is equal to torque 2. So F3 R3 is equal to F2 R2, and solve for F2, putting in all the other values. The question is also asking you to find the force applied by the bolt. Then you go for F net is equal to 0. First was tau net is equal to 0. This means tau net is equal to 0. No rotation. F net is equal to 0. Then you'll go as up forces, cancel down forces. And after you solve this, you should find the fulcrum force, or as I called it, F2, to be 946.43 if you want to be more accurate. And the force of, sorry, that was the force of the bolt, not the fulcrum. Try to delete that. I told you the wrong force, sorry. My computer is freezing on me now. Okay, let's delete all of it. Alright, after you do all those calculations, you will find F1, the force of the bolt, to be 946.43 Newton, and force of the fulcrum F2 to be 1476 to 1476.43 Newton. Solve it and find these. This will be a good practice. The last question I want to solve is, this is also for you. I gave you the answer here. This is simpler than previous two actually. One boy sits here, the other girl sits here. If the distance of boy is 1.6 meters, what is the distance of girl? If the system is in equilibrium, equate the torques. So you'll say tau clockwise is equal to tau counterclockwise. To solve this, and answer should be 1.4. Alright, last question is about non-equilibrium. This is also for you. Do it yourself. Ask me questions if you have questions. And here is another question I want to solve here. This is about non-equilibrium. This topic looks quite complicated, but it's not at all. Actually, we will say, what is tau net? We'll find that. That will be tau counterclockwise. We'll take those as positive, add them all up, and take the difference between them and the tau clockwise. And we will say that tau net is equal to I alpha. That's it. And then if we are asked to solve for alpha, we'll say that's equal to tau net over I. So we'll find tau net, we'll find I, insert them, solve for alpha. Again, alpha is the angular acceleration, and I is the moment of inertia or rotational inertia, also called rotational inertia. This equation again looks like F net is equal to ma. Instead of a linear acceleration, we have now angular acceleration. Accelerations are related. Instead of a mass, now we have inertia. Let's read the question. Josh has just raised 2.5 kilogram bucket of water using a Wells winch when he accidentally lets go of the handle. The winch consists of a rope wrapped around 3 kilogram, 4 centimeter diameter cylinder, which rotates on an axle toward the center. So the cylinder rotates here. It will have an inertia. It will have a rotational inertia or moment of inertia. The tension in the rope is 39.83 Newton. So we are given the tension in the rope. System is moving. We have this tension, and it's a 39.83 Newton. That tension will apply a torque, and we'll have a torque in this direction. That's it. Tau net is only counterclockwise, no clockwise torques. What is the angular acceleration of the bucket? As this cylinder rotates, bucket will be going down. It will have an angular acceleration. I could also find the linear acceleration in an equation I gave you before. If after find alpha, I can easily find A is equal to alpha times R. R here would be the R of this rotating object we have. Now we have a cylinder, and inertia, moment of inertia is not given, but we'll calculate it using 1/2 mr squared. Simple as that. We are given the mass and R. We'll use that to get to the inertia first. So inertia here is equal to the mass of the cylinder, which is 3 kilogram, times its radius squared. Radius is given as 2 centimeters. We'll have that divided by 100, convert to meters, and square it. That's our inertia, and the value you got from there should be a small value, 0.0006 kilogram meter squared. And my tau tau net again will be only tau counterclockwise. Just one force we have, and that force is causing a rotation, so tau net is only that. And that will be equal to the tension force times R. The rotation is about this axle here, so that would be my pivot point. The tension force, if I draw it, we'll see better, is going around the pivot point here and down. So the tension is applying here, perpendicular to R. Let's show R here again. We again have sine phi to be sine 90, which is 1. Let me put that in here as well. Phi is 90 degree, so sine 90 is 1. Ignore it in here. We'll have the tension times R to be the torque, and that's it. Tension is given. Let me go back to blue here. Tension is given to be, so tau net then is equal to tension 39.83 Newton times the radius, which is in meters 0.002, not 0.02, 0.02 meters. And from there we'll get the tau net as a number, and that should be 0.79 Newton times a meter. Now we're ready to insert all these in alpha. Alpha is equal to tau net divided by I. Inserting those values, we found I to be this value, tau net to be that, so we put them in. 0.79 Newton times a meter divided by 0.006 kilogram meter squared, and that's equal to 26.56. That will be rad per second squared. The unit for alpha is rad per second squared. That's it.